Welcome back to the lecture. In this part 3, we will look at the ideas behind the tsunami models, which are normally used for forecasting the tsunamis. The numerical models of tsunami wave propagation are used to analyze the tsunami as well as to forecast the arrival time and height of tsunami wave at different locations on the coast. So, tsunami forecast models are run in real time while a tsunami is propagating in the ocean. Consequently, they are designed to perform under very stringent time limitations because the tsunami warning do not have much time left out once the earthquake occurs. The problem of tsunami propagation is a special case of general water wave problem. So several assumptions are usually made to solve the problem, though some are not valid under certain circumstances. There are three major sources of dissipation for water waves: bottom friction, surface dissipation, and body dissipation of the energy. Often they are not accounted properly, and that brings errors in the tsunami models. In the case of tsunamis propagating on the surface of deep oceans, one can consider that consider the shallow water theory for the tsunami waves, because the water depth, typically several meters, is much smaller than the wavelength, which is typically several hundred kilometers. So, as we have seen during the last two sections, the tsunamis are generated by a sudden seafloor deformation or submarine slumps or slides or volcanic explosions. So, for modeling the tsunamis due to a sudden seafloor deformation, we have to consider two factors. First is, what is the displacement that has occurred on the seafloor, or the magnitude of displacement, and how far it is distributed, or how far the rupture has occurred on the seafloor. So, if we know these two factors, then we can use that deformation as the displacement of the water, and then we can use the wave theory to calculate the propagation of or the estimate the propagation of the tsunami waves. So, usually tsunami generation assumes that the initial free surface deformation is equal to the vertical displacement of the ocean bottom. So, if the ocean bottom has displaced by 5 meters, the tsunami model also assumes that the entire water column has displaced by those 5 meters, and then start estimating as the wave propagates how it changes. So, the first and foremost is how to determine what is the displacement on the seafloor due to the earthquake, or how much that faulting, as I had explained earlier, had the one piece has gone down or has come up, or it is a strike slip. So, that estimation is very important, and several models have been created to determine the seafloor deformation. And one such model, or the simplest solution, I will not say that it is a model, it is more of a solution provided by, it's an analytical solution provided by Okada in 1985. And for most of the cases, this Okada solution that is based on an analytical solution based on dislocation theory in an elastic half space for the seafloor displacement, it works reasonably well. So, in the absence of sophisticated source models, this solution provides the desired results, and most of the tsunami models make use of this Okada solution to determine what is the deformation of the seafloor, and what is the distribution of this deformation on the seafloor along the rupture. To determine the Okada solution, we had to use the seismograms It is defined with certain parameters like dip angle, fault depth, fault dimension, length and width of the fault, and Berger's vector, Young's modulus, and Poisson ratio. Some of them are assumed, for example, Poisson ratio or Young's modulus. We had to assume for that region because we don't have exact measurements, and that might introduce some errors, but more and by and large, it works well. And this picture on the right side here, it defines all those parameters, and these are estimatable from the seismogram which I showed in the earlier section. So the standard practice is transfer the inferred seafloor displacement to the free surface of the ocean and treat that as the resulting water motion. So you have a calm sea or sea at the rest which has been displaced. So the entire water column is displaced, and then treat that as a shallow water situation, and calculate the wave propagation. And the most known models are, one is called MOST model, another one is called Tsunami N2 model, Fun wave, or Comcot, or Cool wave. So there are several models available, and some of them are depending on the kind of equations they use, Bosniak type of equation, or some of them like Comcot and most models, they also bring in non-linearity into those equations. So there are some basic changes. Otherwise, most of the models, they treat them as shallow water equations. So in the deeper waters, for example, a model with a coarser grid is fine, because we are not looking at the details in the deeper water, but it would be advisable if the model has much finer resolution near the coast. So at INCOIS, International Center for Ocean Information Services, we have used another model called Advanced Circulation, or ADCIRC model, usually used for storm surge predictions. This also is a shallow water equation model, and that ADCIRC model we have adopted as the tsunami model. The advantage of that model is that we can have coarser resolution to keep the computational efficiency high in the deeper waters, and as it comes near to the coast, we can have the finer resolution, and it uses the finite element method than the finite difference method used by other models. And we have constructed that kind of a model, and this figure shows how those coarse resolution grids in the open ocean changes to the very finer resolution at the coast. And you can see the one of the snapshot from the model here, how the tsunami wave which generated at this area that gets propagated, I guess that is for the 2004 event, and how the tsunami waves approach the Indian coast. And because it's a finite difference model, we can also set up that, and these are just some of the evaluation or comparison for the validation purpose. The red curve shows the model curve, and the blue curve shows the observations from the coastal tide gauges at different locations: Kochi, Tuticorin, Chennai, Paradeep, Male, Colombo, and Hanimadu in the islands in the Indian Ocean in 2004. And you can see that the model and observed curves are matching very well. So this model we can use to forecast the tsunamis. And because of the finite element capability of that model, we can also use that to determine how much inundation takes place as the tsunami wave approach the coast, provided we know the topography of that region. And the model can be run to find out the extent of inundation on the coast, as this example shows here. And if we can merge that with a 3D GIS with the buildings and other features on the coast, we can also depict how the inundation is, how the buildings and houses gets inundated during that event. So this is how the models can be used, and the tsunami models are very important to carry out the forecast. So we will conclude part 3 here, and we will look at how we will use the information we have put out in first 3 parts and make use of that to provide the tsunami warnings. In the next part, we will look at how tsunami warnings can be generated and provided to the general public. Thank you.